Section 12.5, Triple Integrals, video number 1. Before we move into discussing triple integrals, I'd like to remind you of the progression from single integrals to double integrals so that it will be a natural progression into triple integrals. Now, mechanically speaking, you're going to integrate like you always have. The trick to triple integrals is completely understanding the setup and what you're integrating over. For example, when you first saw single integrals back at the end of Calculus 1, the idea was you had the graph of a function y equals f of x, and the motivation was to find the area under the graph by partitioning the interval from a to b into so many subintervals. We're going to call the number of intervals or the number of subdivisions n. And then within each of those subintervals, you chose an x value. So I'm going to let x star I be the random value selected from the ith interval, and then you stuck that into the function to get a y value, which corresponded to the height of this rectangle. The width of the rectangle was called delta x, or delta xi in case they're different. And then the idea or the plan for finding the area under the curve was to find the area of each individual rectangle by multiplying its height, the function evaluated at that randomly selected x value, times the width, the delta x, add up all the areas, and then let n approach infinity. It's worth mentioning that saying that n approaches infinity, the number of rectangles, is not the same as saying that the delta x's approach 0, because I could take one of these rectangles at the end, cut it into an infinite number of rectangles, and the other ones would be just as wide as they always are, unless you explicitly define the delta x, which is normally defined as delta x equals the length of the interval divided by n, in which case letting n approach infinity does force the delta x's to get closer to 0. In some definitions, you will see delta x approaches 0 instead of n approaches infinity. But let's just assume for the sake of our discussion that as the number of rectangles increases, the widths of the rectangles get closer and closer to 0. Anyway, you set up that Riemann sum, and then it morphed into the definite integral of f of x dx integrated from a to b. When you made the transition to double integrals, everything went up a dimension. Instead of your function being a function of one variable, it became a function of two variables. So instead of its graph being one-dimensional, its graph is now a two-dimensional surface. And instead of integrating over a one-dimensional interval, you're integrating over a two-dimensional interval, also known as a rectangle. But the plan of attack is pretty much the same. In order to estimate the volume underneath this surface, but above this rectangle, you could partition this rectangle in both directions, in both the x direction and the y direction. We're going to call the number of divisions in the x direction n, and the number of divisions in the y direction m. And then to find the volume, or to set up an approximation of the volume underneath the surface, instead of setting up rectangles, we bumped it up a dimension and set up rectangular prisms. So within each of these little rectangles down here, once we chopped up the big rectangle, we would select a random ordered pair in the ith row and jth column, if you will. Then we would stick that into the function, and when we stick it into the function, it would tell us how tall that is. F of x ij star, y ij star. And so to find the volume of that rectangular prism, all we had to do is multiply how tall it was, which is what this functional value represents, times the area of the base, delta area. Now that delta area could be thought of as delta xi, delta yj. In other words, how wide the interval is in the x direction times how wide the interval is in the y direction, but together that product makes delta aij. And then we found the double sum, because we had to take the sum over all of the i's in all the partitions in the x direction, and the sum over all of the partitions in the y direction. Then we took the limit as both n and m approaches infinity. In other words, we cut it up infinitely in both directions. We get a better approximation for the volume, we take the limit, and we get the double integral. if this rectangle was defined between a and b on the x-axis and between c and d on the y-axis, then the limits of integration were from a to b for dx and from c to d for dy. Actually, I kind of abused the notation here a little bit. If I'm going to write dA over here, then I should refer not to the limits of integration, but to this rectangle, which I'm just going to call R. But we can do the double integral as an iterated integral. Let me make sure the bottom of the screen is being caught on the video. I think it is. Yeah, it is. So to do the iterated integral, instead of the double integral over the region, we could do the iterated integral, which means that we do two separate integrals. And just for clarity, let me get this set up. dA is dx dy, my x's range from a to b, and my y's range from c to d. The only difference between these two, technically speaking, this guy up here is one integral, called a double integral, and you do it over one region. This guy down here is called an iterated integral. That means you do more than one integral back to back. You do an integral with respect to x, then you do an integral with respect to y. It's easy to tell the difference between technically a double integral and an iterated integral. A double integral has dA, whereas an iterated integral has dx and dy. They kind of mean the same thing. The difference is, really the thing is, how you evaluate a double integral is you do an iterated integral, one integral followed by another. But it's the extension from functions of one variables to functions of two variables. So how do we do a triple integral? Or what's the premise behind a triple integral? Well, we run into a problem when we try to bump everything up a dimension. Not in the function. Y is a function of x, we've got that. Z is a function of xy. What letter do we use next? Well, we'll use w as a function of both x, y, and z. But the problem is we can't draw that function in 3 dimensions. Why? It has 4 variables, and therefore we would need a 4-dimensional picture. Good luck drawing that. So we can no longer draw the thing that we're integrating. One variable, 1 dimension, lives in R2. 2 variables, a 2-dimensional shape, lives in R3. 3 variables, a 4-dimensional shape would live in R4. So, 3 dimensions, a 3-dimensional graph would have to live in R4. And again, we're not going to draw that. Now we can draw traces of this function, meaning if we let w be a constant, then we can graph this solid in 3 dimensions. But we don't really need to sketch the function, we just need to know what we're integrating it over. So if you look at what we've integrated over, back here we integrated over a 1-dimensional interval, it only has length. Here in the double integral, we integrated over a 2-dimensional region, it has length and width. So it's a natural extension to say for a triple integral, we would integrate over a 3-dimensional interval, if you will, which would be a rectangular prism. So what I have drawn here on the board, and it took me a while to make sure it was drawn okay, is a 3-dimensional interval. Not the projection down here on the xy plane, but this box that is defined in the x direction as being between a and b, in the y direction between c and d, and in the z direction between r and s. All you see down here is the projection of this box down into the xy plane. So in other words, this is the rectangle between a and b and between c and d, kind of like it was over here. So how do we wrap our mind around the concept of a triple integral? Well, we kind of do the exact same thing we did in the previous 2 versions, just without the picture. We subdivide this 3 different ways, along the x's, along the y's, and along the z's. I'm assuming all of you know what a Rubik's Cube looks like. Imagine this is a Rubik's Cube, but you cut it in each direction a bunch of times. So for example, let's say in the x direction, which would be this direction, we do n intervals. In the y direction, which is the horizontal direction, we do m intervals. And in the z direction, which is the vertical direction, we'll do, let's use p intervals. So we cut this box into a bunch of smaller boxes. And somewhere in the middle, let's just grab one of those random boxes. If you want to see a better picture of this box cut up, I invite you to look on page 721 of your textbook. But if we go grab one box in the middle, we'll call it the ijk box, meaning the ith interval in the x direction, the jth interval in the y direction, and the kth interval in the z direction. So if this is the ijk box, then we pick some ordered triple in there, which would be xi, we'll put a star by it, yj, we'll put a star by it, and zk, we'll put a star by it. And then we evaluate the function at that point. So f of xi star, yj star, zk star. And then what do we do after that? We multiplied it times something. Here that something was the width of the rectangle. Here it was the width of the interval, the length of the interval. Here it was the area of the small square, the small rectangle that we selected. So bumping it up a dimension, we would multiply by the volume of this box. So we'll just put delta V, ijk, meaning the volume of that ijk box. Then we take a sum, not a single sum, not a double sum, but a triple sum. I didn't mean to run into this, c'est la vie. The i's are running from 1 to n because we cut the x's in n subintervals. The j's are running from 1 to m. I don't know why I did n before m, but oh well. And then the k's, the subscript on the z's, are running from 1 to p. And then we take the triple limit as n, m, and p all approach infinity. And so we get this big mess, but it's the natural extension from what we did in 1 and 2 dimensions. And as long as our function is continuous, I neglected to mention that, on all of these we're assuming the function is continuous and that's all we need, then this limit would be defined as the triple integral over this, we'll put a capital B for box. Although, as you'll see later, the solid over which we're integrating does not always have to be defined so conveniently. It can be defined on two opposite sides, top, bottom, left, right, front, or back, by surfaces. But the triple integral over this box of the function f of x, y, z, dv. And again, that is a triple integral. But the way you evaluate a triple integral, or rather one way to evaluate a triple integral, is to write it as a iterated integral. 3 back-to-back-to-back integrals. So we're going to do 3 integrals separately. And if we're integrating over a box, a rectangular prism, it really doesn't matter what order the dv occurs in. Let's just do dx, dy, dz. Later, as you'll see, switching the order of integration can cause some headaches, unless it's a box. Because the surfaces that define all 6 sides of the box are constants, so it doesn't matter which perspective you look at. We're going to integrate the x's over a to b, integrate the y's from c to d, and integrate the z's from r to s. So this is a triple integral, and the technique for evaluating it, at least when your solid that you're integrating over is a box, is to just set it up as a pretty straightforward triple iterated integral in any particular order. We'll take a look at an example in the next video.